Hello, everyone. This is Professor DePaulo going to talk to you about the one sample t-test today. So, as I've described previously, we were using the z-test, which is the standard normal distribution. So, we were using the one sample z. In the one sample z-test, we are comparing a sample mean compared to a population mean. What we want to see is the sample mean different from the population mean. In this situation, sigma, the population standard deviation, is known. So in order to use the one sample z-test, we need to know sigma. The vast majority of the time, we do not know sigma, which is the population standard deviation. So we're going to use t instead. So when sigma is unknown, we are going to use t. Now, t is a little bit different than the normal because it's fatter in the tails and it's basically flatter in the middle. So let's look at what T looks like. So T has got thicker tails and a flatter middle. So you see there's thickness in the tails here, which makes it harder to reject the null. So this is harder to reject the null hypothesis because the tails are bigger. So in other words, in saying harder to reject the null hypothesis, we say it has lower statistical power compared to, say, the one sample z-test. So it has lower statistical power, it's harder to reject the null, and therefore we're more likely not to detect a difference when the difference really exists in the population. And that from last lecture is known as type 2 error. So when I'm using a t-distribution, I'm more likely to have a type 2 error, which is not what I want, because that means my idea works, but I can't find that idea working in the sample. Now, as t gets bigger, t will approach z, right? So when the sample, I mean, it's not as t gets bigger, as n gets bigger. So as n gets bigger, the sample size, as n gets larger, t will approximate z. When you're over 100 or so, t and z are very close together. Okay. The other difference is with z, with the normal distribution, we're only looking at one curve that's always the same. With t, we have a different curve for every different degrees of freedom, right? So as n gets bigger, the curve keeps changing and it becomes more and more like z. So if n is small, we're going to have something like this where we have flat and thicker tails. So this is like n less than 30. And as n gets bigger, right? So this would be like n of 60. And then when n gets even bigger than that, we have a perfect normal distribution and is greater than that, right? So as the sample size is increasing, t is becoming more and more like z. So t is approximating the normal distribution. And around 100 or so for our sample size, our n, there's really not much of a difference between t and it's very small difference. But at lower sample sizes, t is penalizing you compared to z. It's penalizing you because you have to estimate the population standard deviation by using the sample standard deviation. So that estimation is costing you. So I kind of like to think of T as a penalty, right? So T penalizes you for estimating sigma. That penalty gets less as n goes to infinity, right? So as n gets bigger, the penalty decreases. And that's how I always look at T. As n gets bigger, that penalty goes smaller and smaller. And I said over 100, not much of a difference. Now, T uses a concept known as degrees of freedom. These are the number of scores in your sample that are free to vary. And this is a bit of an abstract concept, uh, but it's kind of like if you know most of the information, then the last piece of information gets fixed, right? For example, if you got these scores for your X, 3, 5, 6, 4, right? And you know that the mean is equal to 5, right? And you have one more value here that we don't know. What is this value going to be? Let's call it a question mark, right? This question mark value is fixed. It is not free to vary because we know that the mean is 5. So if we know that the mean is 5 and there's 5 scores, then we know that the sum of X is 25, right? So we know that this column adds up to 25. That means these 4 scores can take on any value they want, but the last score is fixed, right? So this data set of 5 scores only has 4 degrees of freedom because the last score is fixed because of the mean being 5, right? So when we're calculating mean and the variance in the sample, we're always going to have a score that's fixed depending on how many parameters we're estimating. So if I add this up, I get 8, 14, 18. This value has to be equal to 7, right? Because it cannot take on any other value. It's fixed. 7, 11, 17, 22, 25, right? So here we have 5 scores, but only 4 of them are free to change or free to vary. The fifth one is fixed, knowing the mean, right? So think of it like when we do variance and we're estimating the sum of we're estimating the sum of the deviation scores, right? So the sum of x minus m. Remember that the sum of x minus m always equals 0. So no matter how many scores we have, the last score in the data set is always going to be fixed because we know that the sum of x minus m equals 0. These are the deviation scores about the mean. Their sum always is 0, so the last score in your sample is always going to be fixed. It cannot just take on any value. It's going to take on a value that makes this equal to 0. So that's what we mean by degrees of freedom in sort of a simplistic term. If we talked about vectors in geometry and projecting vectors into parameter space, it's going to get a lot more complicated and it's going to be really abstract. But basically, you can project this out into multidimensional space if you want to. But from this simple example, I've shown you that the degrees of freedom is n minus 1. So for the one sample t, the degrees of freedom is n minus 1, the number of people in the sample minus 1. we are only estimating one parameter. We're estimating sigma, right? So we're estimating, I'm not spelling this too well here. We are estimating sigma by using S, the sample standard deviation. So if I'm estimating sigma by using S, the sample standard deviation, we are only estimating one parameter. So the degrees of freedom is always equal to n, the sample size, minus the number of parameters you're estimating. Since we're estimating only S for the sample, the one sample, we're going to have n minus 1. We're only estimating one parameter here. If I have two samples, like in the independent groups t-test, it's going to be n minus 2 because we're estimating both sample standard deviations. But for the one sample test, it's going to be n minus 1. Those are our degrees of freedom. And this is important because this changes the curve. As the sample size gets bigger, the degrees of freedom gets bigger, and the curve becomes less flat and more peaked like the normal distribution. So for every different sample size, we're going to have a different t distribution. And that's the difference between z and t. Z always is the same. There's only one curve. With t will change, the curve will change for every different sample size. But the curve will be very close to the normal distribution when our sample size is large, like over 100. And if it gets larger than that, it's even closer to the normal distribution. So that's basically what t does. And now we're going to look at some of these ones. Okay, so we're about to do some problems on the one sample t-test. And what we're doing is the problems that are located under the worksheets in Brightspace under course materials. So if we go to Brightspace under course materials, you'll see table of contents, chapter materials, and you'll see worksheets. So we're going to do the one sample t-test worksheet. Go back to worksheets here. So where all these problems are coming from. So the first problem here, you were investigating a technique that claims to change the age in which children begin speaking. Population mean is 13 months. A sample of 15 children using your technique has the following scores. And we're going to work on that first problem here. So let's go to the whiteboard. And I'm going to take that problem and copy it into the whiteboard. Try and move it into a good spot here. Okay. So we know that the population mean, that population mean is 13. That represents the null hypothesis. We know that the sample is 15. We do not have sigma. We don't have the population standard deviation, so we need to use t. We have one sample here. So let's write down these scores here. Gonna have to move this a bit. Let's move this a bit to finish off the column here. This is going to be our sum of x. So we're going to add this whole column up. And when you add this whole column up, I get 165. So we know that the mean of the sample is the sum of x over n. In this case, it's 165, and our n here is 15, and that gives us 11 as our mean. So we're going to use 11 here. So I'm going to shrink the screen a bit here to fit it all together. Make it a little bit bigger. A little bit smaller again. All right, so this is going to be x minus m. So we're subtracting 11 from each of these. That's 4. Subtracting 11 from each of these to get the difference scores, deviation scores. Okay, so it seems like I added too many scores here. So we're just going to subtract the excess scores. As I was moving down, I duplicated some of these scores here. So I'm just going to erase this column for now. We're going to do it again here. So that looks like 15 scores. So let's do x minus m again here. Subtract 11. I duplicated some scores because I had to scroll the screen down, and I ended up recopying a couple of scores over, which is something that can happen when you're using a tablet. It's not like using a piece of paper. Now this should add up to 0. So negative 2, 5, 11. So that is equal to 0. This is obviously equal to 165. And now we're going to square these deviation scores. And we're just finding the variance again. So that variance problem from exam 1 is showing up again. 9, 4, 1, 16, 49, 36, 1, 0, 16, 9, 1, 0, 9, 4, 1. This adds up to 156. So these are the sum of the square deviations, otherwise known as the sum of squares. So we know that variance equals the sum of squares on the top, which is this column at the bottom here, 156, all over n minus 1. So that's 156 over n minus 1. N is 15. 15 minus 1 is 14. And that will give us 11. So 10, 154, 11.14. That is our variance. Now to find the standard deviation, just take the square root of that. And that gives us 3.34. You may have some rounding going on here. It's okay. Now that we have that, we can plug into our t formula, which is the mean minus the mean of the sample minus the mean of the population over S, the sample standard deviation over the square root of n. So we have 11 as our sample mean. We're comparing it to 13 as the population mean. Our S is 3.34. And then the square root is square root of 15. This gives us -2 on top. 3.34 over square root of 15 is 3.87. So then t is -2 on top. And this fraction becomes 0.86 on the bottom. And that gives me -2.33. That's my final t value. So the question is this significant? Let's look at the hypotheses. Let's look at the null first. The null means no effect, no change, no difference. So this is the technique changes the age at which children begin speaking. So I say the technique has no effect on age of speaking. So basically, the technique does not influence the age of speaking. There's no difference between the new technique and the historical average, which was 13 months, the age. So there's no difference in age. The alternative is non-directional because you're seeing here change. Change is a two-tailed test. You're not giving a direction here. So this is non-directional. Non-directional is two-tailed test. So the technique changes age of speaking. Now you would wonder why did it just say it lowers the age of speaking? Well, they didn't. They're just looking to see if it has any effect at all. So it changes the age of speaking, two-tailed test. So now we're going to look at we have our t value. What we need to have is a critical t. Now, previously you had the critical z-scores, and I gave you those z-scores, right? 1.645, -1.645 for 0.05 one-tailed, 1.96 plus or minus 1.96 for 0.05 two-tailed, and then 2.33 for 0.01 one-tailed, or -2.33, and then 2.58 plus or minus for 0.01 two-tailed. Those are the four critical values of z. They never change. The t value, remember, there's a different t curve for every degree of freedom. So for every sample size, different sample size, there's a different t distribution. So in order to find the critical values, we need a table of critical values. And I provided that table for you under the study guide material. So if you go into study guide here, table of contents, and then I have the study guide right here, chapter material study guides, you're going to see that if you look at formula sheet and tables exam 2, you're going to get the formula sheet and you're going to get the table, the t table you need for exam 2. Here is the t table you need for exam 2. Looks like this. T distribution. So we have on the top row one-tailed alpha values, and on the bottom row, second row, we have two-tailed alpha values. So in this case, we're doing two-tailed, non-directional, and we're using alpha of 0.05, I believe. Let's take a look at the problem again. We're using 0.05 two-tailed. So let's do that. So our alpha at 0.05 two-tailed, it's going to be plus or minus because we're using both tails. And we're going to go to the sheet and look it up. Now our degrees of freedom here is n minus 1. So our degrees of freedom is 14 because n is 15. We want two-tailed 0.05. So we want the second row. We want 0.05 in the second row here, the bottom row. And we want degrees of freedom 14. And we get right here 2.145 plus or minus. 2.145 plus and minus. Remember, non-directional, we have two critical values. So draw the curve. We're out here at negative 2.4. That's a critical value. And then we're all the way over here. Those are pretty large critical values. And we're here at negative 2.33. So we're all the way out in here. So we're all the way in the tail. So since the obtained value exceeds the critical value, it's in the tail, we're going to reject. So if obtained value is more extreme than critical value, sorry about that, typo. Reject the null. So we are rejecting the null here because negative 2.33 is more extreme. Actually, it's not more extreme. Oh, no, this is written. Sorry, I made a little typo here. This is negative 2.145, not 415. So negative 2.33 is more extreme than negative 2.145. So we are rejecting the null. So that's the first problem. Reject the null, support the alternative. So the technique changes the age of speaking. Next one. Move this up. We're now going to look at the second problem here. So a researcher believes that in recent years, women have been getting taller. She knows that 10 years ago, the average height of young adult women living in their city was 63 inches. She randomly samples 9 young adult women currently residing in her city and measures their heights. These are the data. Okay, let's, I just want to maximize the room I have here. So here are my X values. These are 9, right? 4, 5, 6, 7, 8, 9. So n is 9. Degrees of freedom is n minus 1. So that's 8. And we're comparing it to a population mean of 63. We don't know sigma, so we have to use S. We have to use the sample standard deviation, and we must use T. So first things first, add up this column, get our sum of X. When we add this up, we get 576. So we need to find the mean, which is going to be sum of X over N, which is 576 over 9. And when I do 576 over 9, I get 64. And that's a nice round number to use here. 64. So subtract 64. Says this is a nice round number. We're going to do the deviation scores again. Subtract 64 from all of these. Add these all up. You get 0. And then square them all. and get the sum of the square deviations. We add these up and we get 50. So that's our sum of squares right there, 50. Sum of the square deviation scores is 50. We know that the variance is equal to the sum of the square deviation scores over n minus 1. So that's going to be 50. N minus 1 here is 8. That's going to be 6.25 as my variance. And then to find the standard deviation, take the square root of that. When I take the square root of that, I get 2.5. And I'm ready to plug in for t. So we're saying once again, t is m minus mu over s divided by square root of n. So m is 64. The null hypothesis mean is 63. So I'm right away, I'm very close to the null hypothesis. That's not good. That's not what I want. S here is 2.5 and n is 9. So it's the square root of 9, which is 3. This is 1 on top. This is 2.5 over 3. And that's 1 over 0.83, which gives us 1.20 rounded as my t value. That's a pretty small t value. I need to compare that with t crit. Let's find our t crit from the table. And we are using 0.01. Now, is this one-tailed or two-tailed? Well, it's talking about getting taller. Women have been getting taller, so that's one-tailed. So we want a one-tailed critical value at 0.01, or alpha is 0.01. So let's go into the table. Alpha 0.01, right up here, the top row, one-tailed, 0.01. Degrees of freedom is 8. We get 2.896 positive because we're expecting these women to be taller. We're looking in the right tail, taller. So we're looking for a positive value. So it's positive 2.896. So positive 2.896 is my critical. My obtain is positive 1.2. That's not good. Let's take a look at the curve. Sorry about that. Oops. Let's draw the curve here. This is a T curve. It looks like a normal curve because I don't want to draw the flat curve. It's the same thing though. Imagine it's the T curve. 2.896 positive is way out here in the tail. My obtained, this is 0, right? 0 is right in the middle. My obtained value is 1.20. So my obtained value is somewhere in here, right? So since my obtained value is not more extreme, it's not in the tail, right? It's not more extreme or not in the tail of the critical value, we're going to fail to reject the null here. And we say that there is no effect in terms of the height, that the heights have not changed. So the heights of women in this area are no different than they were 10 years ago. So whatever idea they had that heights were increasing is unfounded. It's not correct. And we're done with T. One sample T, that is. Now I want to talk a little bit about something called a confidence interval. So far, we have been doing what is called a point estimation. So we are taking a sample mean and we are comparing it to a specific population mean that represents the null hypothesis. And our hope is that our sample mean is different, either greater, less than, or somehow different than the historical population average, or the null hypothesis population mean. So we're comparing our sample mean to one specific population mean. That's what we've been doing for the one sample Z and now for the one sample T. The confidence interval is a little bit different because it kind of works backwards. It takes your sample mean and your sample variance and it provides you an interval where the population mean is located in. Okay. So most of the time we're either doing 95 or 99%. So in a 95% confidence interval, we are going to have a lower bound and an upper bound. We're going to have two scores, a lower range and an upper range, right? Lower score and upper score. And we are certain that there is a 95% chance the true population mean of the sample there's a 95% chance the true population mean of the sample is in this interval. So whatever these scores are, there's a 95% probability that the mean of the population for where the sample is drawn is within this upper and lower boundary. And when I do 99% of lower and upper boundary, then I'm obviously 99% sure the population mean is located within those two, within this interval. The population mean falls within this interval. So we're not directly comparing a sample mean to a specific population mean. I'm giving you a range, or the confidence interval is giving you a range where you would find the actual population mean from which the sample was drawn. Falls in this interval. Obviously, if you have a 99% interval, the interval is going to be wider than a 95% because you're giving more confidence that the population means within the interval. So if you're more confident the population means in the interval is going to be wider. If you're less confident, the interval could be smaller, but you're not as likely to find the population mean if the interval is smaller, right? So there's a kind of kind of offsets itself. So a wider interval for a higher confidence. Well, why this is good is because you can compare all the population means. Like, for example, let's say that you had a 95% CI confidence interval between 6 and 16. So you're measuring something and you got the 95% confidence interval of 6. So 6 is the lower end, 16 is on the upper end. Now, I want to compare this to a different population mean. So I want to ask you, is this sample from a population different from 12? A population with a mean of 12. And you look that 12 is in this interval here between 6 and 16. So this sample is probably from a population with a mean of 12. This sample would be likely from this population. So we say yes. Is it from a population with a mean of 6? Once again, 6 is in the interval. You're going to say yes. How about a mean of 20? 20 is not in this interval. So you're going to say no. So if I'm comparing this sample against a population mean of 20, I'm going to say that this sample is probably not, most likely. I'm 95% confident that this sample, the mean of this population that the sample is drawn from is not 20. It's less than 20, right? That's another way of testing a hypothesis. So I'm 95% sure that my population mean of the sample is not from a population with a mean of 20. So there is a significant difference here between this sample and a parameter value of 20. right? So if the population mean is within the interval, then this sample is most likely drawn from these populations, right? These are the same populations. But if my interval is different from the population mean I'm comparing it to, then we're going to say that it's statistically this sample is statistically different from a population with a mean of 20. And I'm going to reject the null hypothesis. So whenever you see an overlap between the interval and a point, you're given like a mean here of a population, you're going to say not statistically different, significant. And then if you see it outside of this interval, you're going to say statistically significant. Now this is 95. So 95% corresponds to an alpha of 0.05 two-tailed. Confidence intervals are always two-tailed. So our confidence intervals are always going to be the two-tailed variety. So we're always doing a two-tailed test here because we have a lower boundary and an upper boundary. So we have, by definition, two tails here, or 2 points of delineation to cut off the tail. So the 95% confidence interval corresponds to an alpha of alpha 0.05 two-tailed. A 99% confidence interval corresponds to an alpha of 0.01 two-tailed. So if our parameter that we're testing against is not in this interval, we can say it's statistically significant at the 0.05 value if it's 95%, or the 0.01 value if it's 99%. So here, a mean of 20 of a population mean of 20 is statistically different from this sample at a 95% confidence interval. That translates to 0.05 two-tailed. So I would reject the null at 0.05 two-tailed. If this was 99, I would reject the null at 0.01 two-tailed. And so it's a little bit of a different way of testing a hypothesis, because now we're not just testing against one value. We can test this interval against many different values and determine if it's statistically significantly different, if it's significantly different from those population parameters, those population means. So it gives you more flexibility like this. And you often see the confidence interval along with, not in replacement of the hypothesis test. So you're going to see the t-test, you're going to see a significance value, and then a lot of times you're going to want to add a confidence interval to provide more information for the reviewer who's reviewing your paper, your analysis. So confidence intervals are pretty easy to generate, and they are interesting things to look at. So let's take a look at how to compute a confidence interval. I'm just going to use a little bit different formula. Remember that the confidence interval is always going to use a t-value if we're using t. If we're using t, it's going to have a t-value that's always two-tailed. And the value for t is always going to be positive for the confidence interval. So let's take a look. So the next problem here, if you go to worksheets under confidence interval for t, you'll see the next problem that we're going to do. We are looking at a 10-point math quiz. What do I do now? Here's our 10-point math quiz. So these are the following scores. And so here's my X values. I'm going to put these scores in a row here. Let me get rid of this. So one thing about tablets are things pop up on the screen, and it's really annoying dealing with that all the time. 2, 4, 7, 6, 4, 2, 1, 10, 9, 7, 9, 8, 0.8766. And we're going to get a sum there. So this is n of take a look at the original problem here. See what the n is going to be. So I'm just going into the original material here. Worksheet, let's sample t-test worksheet. Wrong worksheet. We're doing confidence interval. Right below that. So 2, 4, 7, 6, 4, 2, 1, 10, 9, 7, 9, 8, 8, 7, 6, 6. You always got to check because the n here is 16. When you got like a long list of digits here, you want to check to make sure you typed it correct. If I add up the sum of this column, we're going to get 96. So we know the mean is equal to 96 over 16. The mean is going to be 6, a nice whole number again. My degrees of freedom is n minus 1 here. So it's going to be 16 minus 1 is going to be 15 degrees of freedom. So if you want to look at the formula for t, for the confidence interval, we're going to be doing a 95% confidence interval here. It's going to be m plus and minus our t value from the table times the standard deviation over the square root of n. This t value from the table is always positive t value, never negative. Always positive t value for a confidence interval. It's important to know that. Now let's do x minus m, because we're calculating, once again, we're doing the variance problem, a standard deviation problem. Subtract 6 from each of these scores. And when they add this up, we get 0. And then we're going to square this column. These problems are a little bit longer than I would ask you to do on the exam. So add up the sum of squares, I get 110. So our variance is going to be 110 over n minus 1, which is 15. So the variance is 7.33. Taking the square root of that to get the standard deviation gives me 2.71, which is the value I need. Now we're going to plug in here. Our mean is 6, plus and minus. Now the t value. Our degrees of freedom 15. The t value is always going to be two-tailed for confidence interval. So it's always two-tailed. And since we're using 95, our alpha value is going to be 0.05. If we have 99, then our alpha value is going to be 0.01. So with 95, our alpha value is it adds up to 100. 95 and 5 gives us 100. So 95, you're going to have 0.05. Two-tailed. So 0.05 two-tailed with 15 degrees of freedom. So find 15 degrees of freedom in the table. Find 0.05 two-tailed. Bottom row is two-tailed, 0.05. 15 degrees of freedom gives us 2.131. Always give the positive value. Always positive. 2.131. 2.131 is our T crit. Our T value we're using. So this is 2.131 times S, which is 2.71 divided by square root of N. That's going to be the square root of 16, which is going to be 4, right? So 6 plus or minus this value, the T, times 2.71 over 4. Then if I make some more room here, this is going to be 6. Forgot the plus or minus now. Let's go back to do 6 plus or minus 2.131 times this value, which is 0.6775. So that's 6 plus and minus this, multiply these two values together, and that gives us 1.44. And then we're going to put it into a bracket. The lower value, which is 6 minus 1.44, is 4.56. 6 plus 1.44 is 7.44. And there's your 95% confidence interval. So what this is saying is that the true population mean, so the population from which this sample was taken, has a mean between 4.56, 7, and 7.44. We're 95% sure of that, 95% confident that the mean of the population from which this sample was taken is between these two values. So if I was comparing it against a population mean of 9, right? And I said, is this sample significantly different from compared to a population with a mean of 9? 9 is not in this interval. So if I'm comparing it to a population mean of 9, I would say it's statistically different. It's statistical significant, right? At the 0.05 level, because it's a 95% confidence interval. That this sample is not from this population. I'm 95% sure. So I would say reject the null, that the sample is significantly different from a population of 9 with a mean of 9. For instance, if instead I was doing a mean of 6, well, the mean of 6 falls within this interval, so I would say it's not statistically different or not statistically significant when compared to a population of 6 with a mean of 6, right? So here I'd say different, here I'd say not different. So reject the null with 9, fail to reject the null with 6, if I'm doing that. Okay. And I think what I had was the population of, let me see what the problem says. Sorry, I zoomed out for a minute. Population of 8. 8 is not in this interval. So since 8 is not in this interval, I would say that it's statistically different. That this sample is statistically different than a population mean of 8. Because 8's not in the interval. So that's a 95% confidence interval. Let's try a 99% confidence interval. So here's some data. So we want to find a 99% confidence interval for this sample, of the mean for this sample. So how many points, data points? 1, 2, 3, 4, 5, 6, 7, 8, 9. Mean is going to be sum of x over n. So let's find the sum of x, 90. 90 divided by 9 Mean's gonna be 10. Nice whole number again. See, I'm being very nice about the nice means I'm giving you. And expect the same on the exam. I'm not gonna make you struggle. I'm gonna try to make it as basic as possible for you, uh, so you understand the concept. I'm not gonna make you go crazy with decimals. At least that's not my plan, right? And if you remember exam one, I did make you go crazy with decimals. Subtract 10 from each of these values. This column will add up to 0 if you did it right. It does. Make an x minus m squared column. Square these deviation scores. This is 114. Now compute the variance. So the sum of squares, which is 114, is on top. N minus 1. So degrees of freedom here. N minus 1 gives me 8. So this is over 8. This gives me 14.25. And take the square root of that to get the standard deviation. And that gives me 3.77 as the standard deviation. I need that. Confidence interval for 99%. Same formula, mean plus or minus the two-tailed t-value that's positive. Two-tailed t critical value that's positive, two-tailed t-value at 99%. So this is 0.01, right? This is 0.01 two-tailed. Before it was 0.01, 0.05. For 99, it's 0.01 times s divided by square root of that. So let's do that. Mean is 10. I need that 0.01 two-tailed critical value of t. So degrees of freedom are 8. So we're going to find 8 on the side here. It's two-tailed, so it's always the bottom row. And it's 0.01 two-tailed, so it's all the way to the right here. At 8 degrees of freedom, 3.355. So this is 3.355, always positive, this value. S is 3.77, square root of 9. So that's going to be 3, right? So our CI is 10 plus or minus 3.355 times 3.77 over 3. So that's going to be 10 plus or minus 3.355 times this simplified is 1.257. Like I said, if you round a little bit, you're going to be a bit off. So, I mean, I like to keep the 3 decimal places, but if you round it 2, it's not going to be that far off. It's okay. 10 plus or minus this product, which becomes 4.217. And then so the lower boundary, 10 minus 4.217 is 5.78 rounded. And 10 plus this is 14.22 rounded. There's my 99% confidence interval. So if a population mean is outside of this interval, then we have a statistically significant difference at the 0.01 level, two-tailed. So let's take a look. I'm comparing this to a mean of, well, this is the math. I didn't post this one. Oops. Sorry about that. I didn't post the problem. The problem is here in, right here, problem 2. This is sleep clinic. These are hours of sleep. Oh, no, these are awakenings. So what's the 99% confidence interval? We just found awakenings. Is it different than mean of 6? So is this sample mean of this sample? Is the mean of the sample significantly different than the mean of 6? And so is 6 in the interval? It is. 6 is in the interval. So this sample is not statistically different from a population with a mean of 6, because 6 is in the interval. If it was a mean of 5, it would be statistically different from a population with a mean of 5, because 5 is not in the interval. But since 6 is in the interval, it is not statistically different from a population with a mean of 6 at the 0.01 two-tailed level. That's based on the 99% confidence interval. And that's pretty much an alternative to hypothesis testing is do an interval estimation, which is a confidence interval. And it gives you a wide variety of, it gives you more flexibility in testing against different means. So you're not just comparing one mean to one sample, you're comparing a sample to a variety of means and determining whether or not the sample is significantly different from the variety of means that you're comparing it to. So it gives you flexibility. Instead of doing multiple p-tests, you could do one confidence interval and then do the hypothesis testing based on that confidence interval. And so it's kind of neat in that way, and it's useful analysis technique. And a lot of researchers, a lot of reviewers that you submit to will, and I'm one of the reviewers, that when I'm asked to review a paper, I'm looking for things like the confidence interval. I'm looking for really good data analysis. So this is something that's useful to report in your research. So that's it for one sample T and confidence intervals with one sample T. So hopefully that helps. If you have any questions, let me know, or talk to me in class, or you can come to my office hours, you can send me an email, whatever you want to do. So hopefully that helps you. Bye for now. See you next time.